Hello everyone. So now we will see the series and parallel connection part. Okay. So this is a general form. Okay. Not specific to inductor, capacitor or resistor or transistor anything. We will see those form again. But let's see a general form. So whenever some elements are connected in series, what does that mean? That means that all the elements will be having the same amount of current. Okay. When the elements are connected in series, that means that all the elements will be having the same amount of current and different voltages. Okay, that means the current is the same. Here current I, here also current I, here also current I, but the voltages would be different. Here we will have V1 voltage, here we will have V2 voltage, here we can have Vn voltage. So what does series connection means? Series connection, that simply means that current same and voltage different. Okay, it's not just specific to resistance or transistor or capacitance or inductor. It's specific to anything. Let's say someone is saying that you have two systems in series. What does that mean? Two systems are in series. What does that mean? That means they are connected like this. Two systems are in series. That means they are connected like this. And for systems we can call it cascade as well, that we will study later on. So but this is the series connection. Okay, because the current would be the same. And when someone says two elements or two systems are in parallel, this is what they mean. That means that the current will be the different one. Here we can have IN current, here we can have I2 current, here we can have I1 current. Okay, but the voltage will be the same. This V voltage, this voltage I am talking about, this V voltage will be going up to all the elements. So this will be having V voltage, this will also be having V voltage only, and this will also be having V voltage. So what does parallel connection mean? So parallel connection simply means same voltage and different current. Like two systems can be connected in such a way, like in this way it will be connected. In two-port network we will see this, that the voltage across them would be the same. This V voltage will be the same, both of them, but the current they are taking are different. Okay, so we will see those circuits, we will see those configuration, but basically parallel connection means voltage same, current different, that's it. Okay, so this is the parallel connection. Now there is a simple note you should see, like we studied about the capacitance, we studied about the inductance, right? So are they the impedance? No, they are not the impedance. We have studied about the resistance. Yeah, that is an impedance. So the impedance provided by a resistance is R always. Now impedance provided by an inductor, what will be the impedance provided by an inductor? That will be j omega L. If you know it already, then it's good. If you don't know it, you should note it down. It is j omega L. And what is the impedance provided by a capacitor? It is 1 by j omega C, or 1 by j omega C, or you may write it minus j by omega C. J goes up, so minus sign. So minus j by omega C. Okay. So these are the impedance provided by the inductor and the capacitor. And by resistance, this is R. And all of them will be having the unit of ohm. Right? R is having a unit of ohm because the impedance has the unit of ohm only. Impedance has the unit of ohm only. Okay. Now let's look at the formula of equivalent resistance, equivalent inductance and equivalent capacitance in case of series combination. So this is a series combination, right? All of them will be having the same current, I current. Because of this I current, this will have a voltage drop of IR1 in this direction. This will have a voltage drop of IR2, and like that this will also have a voltage drop of IRN. Now I am replacing this circuit with the equivalent circuit of this. So first I will write KVL for this. What will be the KVL? V equals to IR1 plus IR2 plus IR3 plus dot IRN. Did you understand it? I am starting from here. 0 plus V minus IR1 minus IR2 minus IRN. So all of them will be minus. So I put it ahead of the equal sign. So V goes to IR1 plus IR2 plus IR3 plus dot 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 IRN. Now for this circuit, for this equivalent circuit, V is equals to I into R equivalent, right? So I into R equivalent is equals to IR1 plus IR2 and so on. Basically your R equivalent is R1 plus R2 plus R3 till Rn. Okay. This is your final formula of R equivalent for series connection. This is very basic thing that we studied in 10th class. I guess most of you already know it. Okay. So this is the equivalent resistance. Now talking about the inductance, same thing we are doing for inductors as well, connected in series. Ln I should write, not L4. We connected all those in series and applied a voltage. So and there will be a current I. So in all the inductors there will be same current, right? This I current will be there. So what I can write V equals to L1 di by dt plus L2 di by dt plus L3 di by dt, like that Ln di by dt. Also here when I replaced it with L equivalent, when I replace the complete this combination, in this one I replace this combination with R equivalent. Okay, this complete configuration with R equivalent. Here as well I am replacing this complete configuration with L equivalent. So what I can write, V equals to L equivalent di by dt equals to L1 di by dt plus L2 di by dt and so on Ln di by dt. So basically what is the formula of L equivalent now? Because di by dt will get cancelled. So it will be L1 plus L2 plus L3 goes on till Ln. So this is same as resistance, right? This is same as resistance. Now try doing the same for capacitor by your own. Write down the equation. V equals to what is V equals to? All of them will be having the same current, right? And different voltage. So V is equals to 1 by C integration 1 by C1 integration I dot dt plus 1 by C2 integration I dot dt plus 1 by C3 integration I dot dt and so on 1 by Cn integration I dot dt. Now here in this question, in this circuit, what you can write? V equals to 1 by C equivalent integration I dot dt equals to 1 by C1 integration I dot dt plus 1 by C2 integration I dot dt dot 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 1 by Cn integration I dot dt. So basically what is your 1 by C equivalent now? 1 by C equivalent is 1 by C1 plus 1 by C2 plus 1 by C3 and it goes on. This is the answer for series combination. Okay, so in case of capacitance it is not same as R and L. In case of capacitance it is not same as resistance and inductance. Okay, so it is different. 1 upon C equivalent is equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3 and dot 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 1 upon Cn. Okay, now coming to the parallel combination part. Okay, so for parallel combination what will happen? All of them will have the same voltage V. This will also have a voltage V. This will also have a voltage V. So now tell me what will be your I equals to? Here we are applying KCL, not KVL. We are applying KCL here. So your I is equals to, what is the current through this resistor? What will be the current through this resistor? V by R1, right? From high potential to low potential, V by R1 current. And across this, V by R2. So similar way, V by Rn. V by R1 plus V by R2 plus V by R3 and in the similar way V by Rn. Now tell me about this. What will be the value of I here? Here I will be V by R equivalent, right? So similarly, V by R equivalent 1 by R1, sorry, V by R1 plus V by R2, it goes on till V by Rn. So what is the final formula for 1 by R equivalent? 1 by R equivalent is 1 by R1 plus 1 by R2 plus 1 by R3. It goes on like 1 by Rn. Okay, very basic thing, very easy thing, right? Okay, great. Now let's move on to this for inductors. Okay, so again all of them are having the same voltage, V voltage, V voltage, V voltage. So what will be I? I will be equals to 1 by L1 integration V dot dt plus 1 by L2. What is the current through this inductor? I told you about this. If an inductor L is there and there is V voltage across it, so what will be the current? That will be 1 by L integration V dot dt. Or how you can remember? V equals to L di by dt. V equals to L di by dt. So I will be equals to V by L integration dt. Right? I told you about this concept when we were studying about inductors and capacitor. Right? So 1 by L1 in V into dt, 1 by L2 V into dt plus 1 by L3 V into dt, and so on. It goes on like 1 by Ln V into dt. So what will be I? I will be 1 by L equivalent I into dt. 1 by L equivalent integration here as well. Here from for this circuit it will be 1 by L equivalent integration I dt. So 1 by L1, not I dt, it would be V dt, sorry. 1 by L1 V dt plus 1 by L2 integration V dt, and it goes on like this 1 by Ln integration V dt. So 1 by L equivalent is equals to 1 by L1 plus 1 by L2, and goes on till 1 by Ln. Okay, for resistance and inductance it is same. So resistance and inductors are brothers. Okay, resistance and inductors are brothers. Resistance inductor भाई भाई और capacitor उनसे अलग. Okay, in case of capacitor what do you see? The series combination of capacitor is equivalent to the parallel combination of resistance. Do you see that? So in all the analysis we will study now, everywhere the capacitor will behave exactly opposite of resistance and inductance. Resistance and inductance will behave same and capacitor will behave exactly opposite. Okay. So what do you think? What should be the C equivalent for parallel combination of capacitor? C equivalent for parallel combination of capacitor. What do you think? What will be that value? C1 plus C2 plus C3 and Cn. Right? In parallel, it will behave as series of resistance and inductor. Okay? We will derive it. All of them are having same voltage V. Right? So I will be equals to C1 dV by dt plus C2 dV by dt, and it goes on till Cn dV by dt, and also I is equals to C equivalent dV by dt. So from here we can conclude that your C equivalent is C1 plus C2 plus C3 and so on till Cn. Very basic thing these are, right? Very basic thing, right? So till now we have studied the series and parallel combination. Okay. Now this is one thing that we should remember. Okay. If there are two resistors connected in parallel, so how will you write the equivalent resistance? 1 upon R equivalent is equals to 1 by R1 plus 1 by R2, right? So 1 by R equivalent is equals to R1 R2 R1 plus R2, right? So from here R equivalent is R1 into R2 upon R1 plus R2, right? So what is your R equivalent? R equivalent is R1 R2 upon R1 plus R2. So you need to remember it. Whenever there are two resistance connected in parallel, what you will do? R1 R2 upon R1 plus R2. Multiplication of both upon addition of both. Okay? You need to remember this formula. It will make your calculation easier. And for L1 L2, what will be the formula? L equivalent. That would be L1 into L2 upon L1 plus L2. Right? Because resistance and inductors behaves the same. And for capacitor, what will be C equivalent? You tell me. For parallel combination, what will be C equivalent? C1 C2 upon C1 plus C2. No, it will simply be the addition. Right? Why so? I just derived it. That's why. We just derived it here. For parallel combination, it is C1 plus C2 plus C3. So the two are connected. So it is basically C1 plus C2. That's it. Okay. If they were connected in series, then that would be the formula C1 C2 upon C1 plus C2. So I can write it here as well. Capacitors in series. This is C1, this is C2. So what will be your C equivalent now? Your C equivalent will be C1 C2 upon C1 plus C2. Okay. So just remember this. Okay. Well and good. Now we will see something that you haven't studied in 10th, 11th or 12th standard. This is source transformation. In BTech first year you must have studied it, but not in 11th, 12th. So sorry, this is not source transformation. This is star to delta conversion. Source transformation is a different thing that we will study. So this is star to delta conversion. So what we are doing is basically, this is a star connection, right? This is looking like a star. So this is what we call star connection, and then we are converting it to a delta connection. Delta is like this. This is delta and this is star. Okay. So we are converting a star to delta. Okay. So basically, this is node A. Let's call it, this is node A. This is node B and this is node C. So between node A and B, we are connecting one resistance. Let's call it Z1. No, forget it. Don't call it anything. And between B and C, we will get some impedance, and between A and B, we will get some. Between A and C, we will get some impedance. So these Z1, Z2 and Z3 are impedances. Okay. Z1, Z2, Z3 are impedances. So basically, we are converting this configuration into this configuration. They can have some value. Let's call this one as Z1 dash, this one as Z2 dash, and this one as Z3 dash. So they will have some value. What will be the value? So you can derive it. Okay. If you want to see the derivation, go to YouTube. You can see the derivation anywhere. There will be hundreds of videos for this derivation, but it's not that necessary. So that's why we are not. That's why we are not deriving it here. So what will be with the value of Z1 dash? So when we are going from star to delta, okay. So this resistance corresponds to Z1 dash, right? So this will be, the value will be multiplication of all the resistance, all two resistance, Z1 plus Z2 plus Z2 plus Z3 plus Z1 Z3 divided by what? We are talking about this resistance now. So what is the resistance in front of that, or impedance? What is the impedance in front of in front of this Z1 dash? That is Z3 divided by Z3. Or what you can see, we are connecting this resistance, this impedance between node A and B. We are connecting this impedance between node A and B. So which resistance is not connected to node A or node B? This resistance, this impedance Z2 is connected to node B. This impedance Z1 is connected to node A. This impedance Z3 is not connected to node A and B by any means. So that's why this in the denominator part Z3 will come. Now try writing for this. For this as well, Z1 into Z2 plus Z2 into Z3 plus Z1 into Z3. Divide by what? You tell me. We are converting it between B and C. We are converting it between B and C. So which impedance is not connected to node B and C? Only Z1. Or which impedance is in front of that? That is Z1. So here we will have Z1. Now what about this? Z1 Z2 plus Z2 Z3 plus Z1 Z3 divided by what? Impedance in front of that, that is Z2, or the impedance which is not connected to node A and C. So only impedance that is not connected to node A and C is Z2 only. So this is how we write it. Did you get it? Easy? Easy to remember? No, it is tough to remember. So how will we remember it? So you are going from star to delta. Star to, let's look at the screen, look at me, star to delta you are going. So you are getting out of it. If you are getting out of it, that means something will get enhanced. घर से बाहर जा रहे हो तो कुछ तो वृद्धि करोगे ना, कुछ तो बड़े होगे ना, तभी घर से बाहर जाओगे. So you are getting out of it, so something will get enhanced, so the formula will be bigger, and when we will convert delta to star na, the formula will be shorter. Okay, we are converting star to delta, the formula will be bigger, and when we will convert from delta to star, that means we are getting into it. If we are getting into, it will be smaller. If we are getting out, it will be bigger. Okay, बाहर जा रहे हो तो बड़े हो गए, अब अंदर ही वापस आ रहे हो, इसका मतलब अभी बच्चे ही हो. So this is what I mean. Okay, so we are getting out, so it will be like Z1 into Z2 plus Z2 plus Z3 plus Z1 Z2 divided by Z3. Okay, so this term will be constant in all the thing, and then we need to see by what factor we will divide it. So that's how we will see. Okay, now if Z1 equals to Z2 equals to Z3 equals to Z, so basically this is your configuration now. This is node A, this is node B, and this is node C. So this is equals to Z, this is equals to Z, and this is equals to Z. So finally, if we are converting it to delta, what will happen? Try putting in this formula. Z1 into equals to Z2 equals to Z3, then Z square plus Z square plus Z square by Z. That means it will be 3Z. Okay, so it basically will be 3Z. This also will be 3Z, and this also will be 3Z. So people sometimes remain confused that it will be 3Z or Z by 3, because in star conversion, because in delta to star conversion, we will see that it will be Z by 3. So people get confused whether it will be 3Z or Z by 3. So you will always remember, if I am getting out of that, if I am going from star to delta, I am getting out. That means it will get bigger. So from Z2 it will get 3Z, and if I am getting into it, that means from Z to Z by 3. Okay, if I am getting into it, it will get smaller. So from Z to Z by 3. Okay, so that's how you will remember it. We will see that in delta to star conversion. Okay, so now tell me the for resistance what will happen. We just need to convert it to star to delta. Okay, what will be the value here? Tell me. At this point, what will be the value? R1 R2 plus R2 R1 plus R2 R3 plus R1 R3 divided by R3, right? Because we are connecting between these two, so this is the in front of this is in front of this branch. Okay, now for this R1 R2 plus R2 R3 plus R1 R3 divided by what? No one should get it wrong. Divided by what? R2, right? Now for this R1 R2 plus R2 R3 plus R3 R1 divided by what? Here, this branch. In front of that, it is R1. That's how we will write it. Now, just applying it in the circuit. So you tell me, what will be this value? 3 into 2, 6. Like I am calling this one as R1 dash, this one as R2 dash, and this one as R3 dash. Now tell me, what is the value of R1 dash? That will be 3 into 2 plus 2 into 6 plus 3 into 6. Right? 2 into 3, 2 into 6, 3 into 6. Divided by what? This is the branch between AB. This is the branch. So ahead one divided 6. That is 6 plus 12 plus 18, 36 by 6, 6 ohm. So R1 dash is 6 ohm. What about R2 dash? You tell me, what about R2 dash? This one. About R2 dash. 36 by 3, 12 ohm. And what about R3 dash? R3 dash. R3 dash will be R3 dash will be this. So it will be 36 by 2. Right? 36 by 2. That means 18 ohm. So basically 6 ohm, 12 ohm and 18 ohm. Right? Now tell me for this. Let's call this one as A, this one as B, and this one as C. So A, B, C. Tell me the value. 3 times, right? Getting out. Same resistance, it will simply be 3 times. 6 ohm, 6 ohm, and 6 ohm. Or you can apply the formula as well. So how will you apply the formula? 2 into 2 plus 2 into 2 plus 2 into 2. So it will be 12 by 2. 12 by 2 is 6. So similarly, for every one, it will be 6 only. Okay. Now let's see for inductor. So like many times we get it wrong, like what everyone will do, like they will make a circuit like this. So we just told the formula that it should have L1 into L2 plus L2 into L3 and so on. So that's right. The final result is fine. But this formula was for impedances, not for this formula was for impedances. Okay. Not for the inductance or capacitance. This was for impedances. So what is the impedance that an inductance provide? So first convert it to this. Okay. Although I have told you one thing, that resistance and inductance behave the same. Both are brothers. So if they behave the same, then there is no worry. But still, j omega L1, right? J omega L2 and j omega L3. Now we will convert it. How will we convert it? Like this. Okay. Like this. Like this. What we will write? We will write, now forget about this, we will write here because it is easier to write here. Okay. So multiplication of all the impedances. So j omega L1 into j omega L2 plus j omega L2 into j omega L3 plus j omega L1 into j omega L3 divided by what? Divided by what? J omega L1, because we are writing here, so divided by j omega L1. So what is the final result that you get? J omega to j omega get cancelled and one j omega is outside. So it is L1 L2 plus L2 L3 plus L1 L3 divided by L1. Because from here we got j omega square and j omega square to j omega got cancelled. So only j omega is left. So basically if you have an inductance of L, it provides an impedance of j omega L. Or you have an impedance of j omega L, it provides an inductance of L. So that means you are having a inductance of this value. Then what is the equivalent inductance here? This is the equivalent inductance, right? For L, you have a impedance of j omega L. If you have the impedance of this much value, your equivalent inductance will be this, right? Understanding it? We won't write for everyone. Now we will finally write the final value. Okay. So whenever there are inductance connected like this, then we can go on and tell the values like this. Okay. So for this one, what will be the value? L1 L2 plus L2 L3 plus L1 L3 divided by what? L3, because this is in front. Now for this one, it will be L1 L2 plus L2 L3 plus L3 L1 divided by what? Very tough to write. Divided by L2, right? And for this one, this is the easier one to write. L1 L2 plus L2 from here to here we are coming. Okay, and this is the final one. L1 L2 plus L2 L3 plus L1 L3 divided by L1. Got it? Well and good. Okay, so basically this from this and then this and this I should. So we just converted first to the impedances, then we saw the formula, and when we saw the formula we got to know it is similar to resistance only. Okay, it is similar to resistance only. So if you know about the resistance, then you can simply write the star to delta conversion. So write down the star to delta conversion for this. It will be 2 plus 3 plus 6. 2 like 2 into 1. Let's call this one as L1 dash. So L1 dash would be L1 dash we are calling. So L1 dash would be 2 into 1 plus 1 into 3 plus 2 into 3, right, divided by this value in front, 3. So 2 into 1, 2 plus 3 plus 6, 2 plus 3 plus 6 will be 11. It will be 11 by 3 Henry. Okay, so it will be 11 by 3 Henry, and for this it will be 11 by 1 Henry, 11 by 1, right, and for this it will be 11 by 2 Henry, right. For this one it will be 11 by 2 Henry. Now think about this and tell me the value. 3J, 2J and 1J. So what will be the value? Again 3, 2, 1. So again it will be 11. So here we will have 11J. Okay, because these are impedances. Here we will have 11 by 2J. And here we will have 11 by 3J. Right? Why 11 by 3J? Because 3 is in front. And 2 into 3 plus 3 into 1. That means 6 plus 3, 9, and 2 into 1 plus 2, 11. So 11 by 3, 11 by 1 and 11 by 2. So it is like that. Now for this you need to make again. Okay. So I guess what I can do is that I can put it here, then I can copy it, then I can make it go here again, then I can paste it. Yeah. So I will just remove it off. Tell me the values for this. You are getting out. Getting out means it will be 3 times. So 9 Henry, 9 Henry and 9 Henry. Okay. Understood? Well and good. Okay. Let's move on to the capacitor one. Now inductor and resistance are brothers, but capacitor always does the opposite thing, and he will do the same here. This is node A, this is node B, and this is node C. You can't really directly write it. We have to convert it into the impedances. Okay. So what do you think? Why is it happening with the capacitor? Because capacitor provides resistance provided impedance of R, capacitor inductance provided resistance of L, but the capacitor provided resistance of 1 by j omega c. Here it is proportional to R, here it is proportional to L, but here it is inversely proportional to C. That's why everything is being opposite with the capacitor. Okay, everything is opposite with the capacitor. Okay, so this is A, B and C. So this will be minus j by omega C1 minus j by omega C2 and minus j by omega C3. So now we will convert it. So I think I should pause and make the diagram. Okay, so we will write for this one. This is A, B and C. So we will write for this capacitor only. Okay, so for this one, first the multiplication of all the capacitances. So minus j by omega square will come out, right? And 1 upon C1 C2 plus 1 upon C2 C3 plus 1 upon C1 C3. Are you able to understand this? What we would have written minus j by omega C1 into minus j by omega C2. So minus j by omega C minus j by omega square would come out and 1 upon C1 C2 would have left. So this is what I have written here, right, for all the terms. And in the denominator, what we would be having? We would be having minus j by omega into 1 upon, for this one we would be having 1 upon C1, right? So what is the final we would be getting? What is the final value we would be getting? Where I should write it actually? I guess I can write it here. So LCM of C1 C2 and C1 C2 C3, it would be C1 C2 C3. So on up we would be having C3 plus C1 plus C2 divided by 1 upon C1. Then the final one we would be getting is C1 and j omega is also there, sorry, minus j by omega is also there, right? Because this is get cancelled, only minus j by omega is left. Okay, and this much capacitance. So what is the final one? Minus j by omega into that C2 will get up and it will be left with C2 C1 plus C2 plus C3, C1 plus C2 plus C3 divided by C1 C3. Okay, so now tell me what is the value of capacitance. If C capacitance was there, you had an impedance of 1 by j omega C1 or minus j omega C. So if this is the capacitance, the reciprocal of this is the, if you take reciprocal of this, then this is the capacitance value. So you have to take the reciprocal of this. So what is the capacitance? So the capacitance here is reciprocal of this value. So it would be C1 C3 upon C1 C3 upon C1 plus C2 plus C3. Did you get it? We started from here, we derived this expression, then we came here. Then we just saw that if we have a capacitance of C, we have 1 by j omega C as an impedance. So if we take the reciprocal of this value, that means we will get the value of capacitance. So now we are just taking the reciprocal of this value, that means this is the capacitance here. So that's how we will convert it. Okay, I guess I did some calculation mistake here. Okay, yeah. It is C1 here. This is C1 here. So we'll be left with C2 C3. Okay, here we will have C2 C3. Okay, so now how will we write it finally? Let's move on to the next page. So in case of capacitance, it is not same as the inductor and resistor. So what will you do? So you are taking between these two. So this is the capacitance between these two nodes, between A and B. So how you will write it? You will write it as multiplication of these two, C1 C2. Okay, I should write a bit above. multiplication of these two divide by addition of all three, C1 plus C2 plus C3. Okay, for this is for this value, and then here multiplication of these two, C1 C3 divided by all the values. So the same thing we will be doing for inductors and resistor, but in delta to star conversion. In star to delta conversion, what we will be doing? In star to delta conversion for inductor and capacitor, what we were doing? L1 plus L2 plus L2 plus L1 L2 plus L2 L3 plus L1 L3 divided by L1 or L2 or L3. So that we were doing. But in case of capacitance, it is not the same. It is opposite. So what we are doing right now, this thing we will be doing for delta to star conversion for inductor and capacitor. Are you getting it? That's why they are opposite. Okay. And for this one, what we will write? C2 C3 multiplication of both of them upon C1 plus C2 plus C3. Now how will you remember it? You will remember one thing. If we are going out, it should increase. If we are going out from star to delta, we are going out, so it should increase. But it is the capacitor. It will increase in resistor and inductor. Capacitor is opposite. Capacitor does the opposite thing. Capacitor हमेशा उल्टा करता है. But it should increase, but in case of capacitor, it will decrease. Okay, so it will be like multiplication of these two divided by the addition of all three. Okay, so this is the final formula. Okay, now tell me the answer for all these things. Let me make it first. Okay, so these are the notes. So between A and B, what we will be having? Between A and B, multiplication of these two divided by addition of all. So multiplication of these two is 6 divided by 6 plus 2 8 plus 3 11. 6 by 11 farad. Here multiplication of these two 18 by 11. Here multiplication of these two 12 by 11. Right, multiplication of these two 12 by all addition of all. That means it will be 11. Now talking about this, you should do it on your own with in paper, then check your answer. So, okay, what do you think? What will be the value of this? Multiplication of these two divided by all means 6 divided by all, 4 plus 3 plus 2, 9. Is this your answer? No, this is wrong. Why so? Because these are impedances, and for impedances we derived the formula. When these are the capacitance, then this formula is applicable. Okay, but for impedances, the same formula, Z1 Z2 plus Z2 Z3 plus Z1 Z3 divided by the in front of 1, okay, divided by some Z. So that formula will be applicable here only. So if we write down for this one, so how will we write down? Let's assume we are writing for this. So what will we do? 8j, the minus j will come out, minus j square will come out. So basically minus j will be here. Then 8 plus 12 plus 6 divided by, for between AB if we are writing, divided by 2, right? So this 8 plus 26 will be above. So 8 plus 12 plus 6, yeah. So 26 divided by something. Okay. So minus j 26 divided by, for this, divided by 2 ohm. For this one, minus j 26 by divided by this value 3 ohm, and for this it will be minus j 26 divided by 4 ohm. Did you get it? Just see it once again. These are the impedances. If these are the impedances, how we will be doing? No matter it is a capacitor, but these are the impedances. If this is the impedance minus j j4, that means it is equal to minus j by omega c. Let's assume if omega is 1, that means your C value is 1 by 4. So here your C value is 1 by 4. If omega is 1, your C value is 1 by 4. Then it will be converted into this impedance. Okay. So this is not the value of capacitance. This is the value of impedance. And for impedance, we will apply the same formula that we studied here. This formula. Z1, Z2 plus Z2, Z3 plus Z1, Z3 upon Z3. Okay. You need to remember it. There is no other way. There is no other shortcut. You just need to remember it. Okay. Yeah. So on the next page, we were doing it. Now for this, same impedances going out, that means it should increase. But this is capacitor, so it will decrease. It will go down to 1 farad, 1 farad, 1 farad. Divide by 3. Okay. Or you can apply the formula as well. What you will do? Multiplication of these two, 3 into 3. Divided by addition of all. 3 plus 3 plus 3. So what you will get? 1 farad only. That's it. But for the same, you should remember it. Okay. You shouldn't derive it again and again. If the capacitance are same, then you should be able to write it in no time. Okay. Yeah. So I hope you are able to understand this. So let's move on to the next thing, that is star delta to star conversion. We studied about star to delta conversion. Now we will study about delta to star conversion. Okay. So what we are doing, this is node A, this is node B, this is node C. We are connecting one Z1 dash in between, then we will have one Z2 dash, then we will have one Z3 dash. Okay, like this. We are converting delta to star. So basically, this we will be forming. I think I should pause it. Yeah. So what do you think? What will be the value of Z2 dash? What we did in the case of capacitor here, when we were writing, let's assume this value, multiplication of these two divided by addition of all. This is what we will be doing. Around Z2, what are the two impedance? Around Z2 dash, what are the two impedance? Z1 and Z3. So multiplication of these two divided by addition of all. What about this one? Around Z3 dash, what are the two impedance? Z2 and Z3. Multiplication of these two divided by all. Z1 plus Z2 plus Z3. What about this one? What are the impedance around Z1 dash? These two, Z1, Z2, right? Multiplication of these two, Z1, Z2 upon Z1 plus Z2 plus Z3. Did you get it? Sure. Well and good. Let's move on to this thing. When Z1 equals to Z2 equals to Z3 equals to Z. So all these are equals to Z. All these are equals to Z. So we are getting into it. That means it should reduce. So it will be Z by 3, Z by 3 and Z by 3. You can also apply the formula. Try applying the formula. What you will get? You will get Z by 3 only. So here you put Z square upon Z plus Z plus Z. So it will be Z by 3. Okay. So it is acting as the same that we saw in case of capacitance. Okay. That we saw in case of capacitance. It is acting as the same only. Okay. Now tell me the values. We will not apply any formula, or we will not we don't need to see it separately now for inductor and resistor, because we know for inductor and resistor it will behave as the same. So it will be 2 into, for this one, 2 into 3, 6 by addition of all, that is 9, 6 by 9, 6 by 9 ohm. For this one, multiplication of these two, 8 by 9 ohm. And for this, multiplication of these two, 12 by 9 ohm. Getting it? Now tell me for this, although it is straightforward, everyone can tell it. Multiplication of these two divided by all. So multiplication of these two, 36 by 18, that means 36 by 18, 2 ohm, or simply by 3, 2 ohm and 2 ohm. Tell me for this one. One inductor here, one inductor here, and one inductor here. Okay, let's forget it. Now tell me for this. 6 into 3, 18 divided by addition of all, 18, 1 Henry. 9 into 3, 9 into 3, what is 9 into 3? 27 by 18, 27 by 18. Or what you can write it, 27 by 18 we will write, you can simplify it. And then 9 into 6, 54 by 18. So it is 3 Henry. Are you getting it? This one, that means multiplication of these two. 54 by 9 plus 9, 18. So 3 Henry. 27 by 18, 1 Henry, 3 Henry. Okay, well and good. Now for this you tell. Multiplication of these two, 18 by addition of all, 18 by 18, 1 Henry. Multiplication of these two by 18, 27 by 18. Okay, this is the same only. And this will be J 300. Now you can do one thing, you can go from here to here as well. How you will go? Applying the same formula, Z1 Z2 plus Z2 Z3 plus Z1 Z3 upon that Z. Okay, like I will tell you the value of this. Apply the same formula, 3 plus 27 into 18 into 27 by 18 into 3, that will be 6 and 27 by 6 we will write, plus addition multiplication of these two, 27 by 18, okay, divided by 27 by 18, and if you do this you will get 6. Okay, if you do this calculation you will get 6 ohm only. Why am I writing Henry here? It should be ohm. Okay, so if you can go from here to here as well. Okay, this is just the conversion, and why is it necessary we will see in some questions. Okay, it will be used at many points. Now for this you already know we are getting into it, so it will be 1 Henry, 1 Henry and 1 Henry. Okay, getting it? Now this note you just read it and tell me if you are able to understand it. Process of star to delta conversion for R and L is equals to the process of delta to star in case of capacitor. Right? This is what I am telling you. It is complete opposite. So now you can guess if we are doing from delta to star in case of capacitor, what will happen? In case of capacitor, if we are doing delta to star, it will be the same as the process of star to delta for RL. I hope you remember the process of star to delta for R and L. Okay. So now tell me, if this one is your C1, this one is your C2, and this one is your C3, what should be the value of this? First, multiplication of all, C1 plus C2 plus C2 C3 plus C1 C3. You can derive it on your own. Divide by what? This node B is connected to these two branches, but not to this branch. Divide by C3. Now similarly, try writing for this. Multiplication of all, C1 C2 plus C2 C3 plus C1 C3 divided by what? For this I am writing, so divided by this C is connected to these two branches but not to this, divided by C1 divided by C1. Now what about this? It will be the same, C1 C2 plus C2 C3 plus C1 C3 divided by what? Divided by this C2 divided by C2. Got it? Now tell me about this. Okay, you can derive it like for previous two things I have derived it already, so you can also derive it, but no need to derive as well. You have to remember these things. Okay, only a few things I will tell you to remember, and this is one of them. Okay, and if you can't remember all these, at least try to remember the similar one when they are connecting Z and Z. So what will be the value? Z by 3, Z by 6, Z by 6. In case of capacitor, it will be 3Z, 3Z, 3Z. So at least remember that. And this formula is not that tough to remember. Okay, because there is symmetry around it. So it is not that tough to remember. Only two things you need to remember. That's it. This formula, this one, Z1, Z2 plus Z2, Z3 plus Z3, Z1 upon the, in front of the, upon front impedance, and this thing, and this formula, the multiplication of two impedance Z1, Z3 upon addition of all the impedance. Okay, this is not that tough to remember. If you practice questions, it will be easy. It will be remembered to you for a very long time. Okay, nobody forgets it. Okay, so let's call these A, B, C. Now write down for this. What you will do? 6 plus 18, 6 plus 18 plus 12 by 6, right? If you are writing here, these two branches are connected to node A, but only this branch is not connected to node A, so by 6. So it will be 6 plus 12 plus 18. It is 36 by 6. That means it is 6 farad. What about this? It will be 36 by 3, right? For this one, 36 by 3. 36 by 3 means 12 farad. And for this, it will be 36 by 2. That means it will be 18 farad. Well and good. Okay. Now for this, do it. You shouldn't do it wrong. Okay. Before writing the answer, just see the question carefully. Okay. You shouldn't do it wrong. Tell me the answer. What will be the value of this? If your answer is like 8 plus 24 plus 12 by 6, then it is wrong. Why so? Because these are the impedances. So basically 8 by 12, that will be your answer. 8 by 12. Multiplication of these two divided by addition of all. Here multiplication of these two divided by all 12, sorry, 12 by 12. Here multiplication of these two minus 24 divided by 12. Like multiplication of these two is 24j square divided by addition of all. What is the addition of all? Minus 12j. So this j and j got cancelled. Okay, it is minus 2j. So this is what we are doing here. Okay. Now for this you need to tell me what will be the value. We are getting in from out. We are getting into it. So it should decrease, but it's the capacitor, so it will increase. So it will get 3 times, or you can apply the formula as well. So it will be 12 farad, 12 farad and 12 farad. A, B, C. Okay, here as well, A, B and C. This is the complete concept. Okay, I hope you have understood it. You can revise it once again. In the next video we will see some questions, so you can revise this thing once again. Let's see again. Okay, this was the very basic thing about equivalent resistance and capacitance that we already know, that for series R1 plus R2 plus R3, for inductance it is L1 plus L2 plus L3, and for capacitor it is 1 by C1 1 by C2, and for parallel this is the formula. Okay, these are the basic things. Then we came to this part that is new to all of you, that is star to delta conversion. Okay, so in this thing what you studied, this is star to delta conversion. So what we are studying is when we are going from star to delta, we are getting out of it. So the formula should increase. Basically formula should increase. That's how we can remember it. So the formula would be Z1 Z2 plus Z2 Z3 plus Z1 Z3 upon the resistance that is in front. So in case of this, the resistance in front is Z3. So similarly we can write it for over, and when Z1 equals to Z2 equals to Z3 equals to Z, then this will happen. Okay, then these are the some question then that we show. Then for in case of capacitor there is one different thing. Okay, in case of capacitor the formula changes, but when we are talking about the capacitance only, when we are talking about the impedance it remains the same. So when we are talking about the capacitance, the formula changes, and the formula changes to this. Like when we are writing down this value, the multiplication of these two divided by addition of all. C1 C2 upon addition of all. C1 C3 addition of all. Then we saw some questions. Then we went to delta to star conversion. So for delta to star conversion, we are getting into it, so formula should reduce. So formula is smaller here. So it is multiplication of these two divided by addition of all. Multiplication of these two divided by addition of all. So this will work only for inductor and the resistance. For capacitance, it will again change. Now for capacitance, it should decrease, but it is the capacitor, so the formula will increase. The formula will increase to what? The multiplication of all the factors C1 C3 plus C3 C2 plus C1 C2 divided by what? The capacitance that is not connected to the particular node. So only C2 capacitance is not connected to the particular node, so it is divided by C2. Okay, in case of this, the in front of capacitor is C3, so divided by C3. In case of this, the in front capacitor is C1, so divided by C1. And then this question we saw. Okay, so these question we saw, and that's how we studied it. Okay, you can revise it once again on your own, and it will be all clear to you. In the next video, we will see some more good questions. Then we will study about equivalent resistance. Okay, the concept of equipotential, bisection, and everything we will study. So we will see very good questions on equivalent resistance and inductance or capacitance in the next video. Okay, then, thank you.